Good, 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 good. So, next step, let's see. Let me open up the stuff quickly. The Google, so we're in the Google, no, sorry, the Circ, this cables, the headphone cables bother me. The VQE, so Google, oh, come on. Let me just disentangle this mess for a second. Yeah, that's way better. So now, Google Circ read the docs. Cool. And so we are at the tutorial part, the VQE exactly. And if I just go into projects and basically this Circ thing here. Okay, so we've got the Circ ansatz, but I think Jupyter. I'm not so sure. Jupyter notebook, is it like that? I think. I don't know which one of those notebooks is the correct one. Might be this one. Let's see. Yeah, that looks good. Because the last point, so we spent the last video basically trying to understand where does the answer come from, and what's the sort of the rationale behind the ansatz, and how does this map to the problem. So the bulk of the video was understanding the problem of the last video, is really understanding the problem. How is this problem here then mapped into this representation of transverse fields and the row J and the column J fields, and then how do we, and sort of understanding those routines where it's like how do we build the ansatz, right? And so I think I mentioned that this part here, the X rotations, where I think we said this was, I said this was sort of related to kind of increasing the space of state space, whatever. I don't know what I said, but I kind of realized that's probably one step to get us into a superposition. Kind of, and then I guess this is one of the things you can tweak, right? Because it depends on what type of superposition you're going to get. Like, it's one of the things that you want to be able to parameterize later on. Then the Z gates were mapping to the actual external fields, and then the control Zs were sort of the ones applied based on the relationship between the different sides. So if you got a +1, it was a control Z, I think it was a -1. You just were first applying an X gate to both qubits, and then control Z, and then another X gate. So you're kind of doing a mirrored operation. We checked that in Quirk as well, and we saw the effect. Anyway, check out the video if you haven't really watched that. So next step is I just wanna. So the next step is I want to go, because now I want to understand why this works, right? I mean, in essence, the ansatz should basically, I believe it should, to some extent, reflect our Hamiltonian, right? Because it should reflect, where is the Hamiltonian? Oh my god. There should be a formula somewhere here. This is scrolling really badly. If I just 2D Isaac model, it was in the Wikipedia. There we had the Hamiltonian that's usually used. Isaac model, exactly. This was the page, and this was the Hamiltonian. What? Where is it? Where is it? Where is it? 3 dimensions, 2 dimensions. This is it. This is it. This is it. This is it. Yeah. Oh, this here. Yeah, but that's the one-dimensional solution. Okay. Yeah, but here there was a when we're talking about the actual problem. Come on, I've seen that. Creating the ansatz. Oh, here. Oh my God, how could I have missed that? The Hamiltonian. Exactly. So, to some extent, that should be related, right? Because, yeah, basically that should be related. But then I don't know how the whole, so what I wanted to explore now is I wanted to explore how does the whole thing, what's the end-to-end result? Because I get that we are going to now run some simulation and we're going to try to find those parameters, but then how do those parameters relate to then finding the actual finding an actual eigenstate or the lowest eigenstate, because eigenvalue, because that's basically what we're after. We're after that value that that basically doesn't get affected by the Hamiltonian. So that's what we're trying to solve for here, right? It's finding that configuration. It's basically finding those things in here. So it's finding those things. Okay, so it's finding the things that basically give us that specific problem configuration. Because I'm not so sure really what we're looking for. So are we trying to solve for just those parameters? Or really are we kind of looking into the actual minimal energy things in here? Or are we just trying to solve for finding the parameters that then give us exactly that model, right? With those interactions, and that's what I'm not so sure. But let's keep reading. So, I mean, this is really simple in the sense that it's just copy pasting, right? So I'm not really. You can see the code here, but it's not. This is just copy paste from that. I can just run the whole thing, and basically we've got now the new circuit in here, which is a bit different than what we have there. And here's we haven't got that parameterized yet. Our problem instance is probably slightly different. It's this one here. Okay, so what's the next step? So the next step is simulation. Now let's see. So you see we've chosen particular parameters values 0.1, 0.2, 0.3. Yeah, but that's a random choice. So now simulation. Let's see how to simulate the circuit corresponding to creating our ansatz. In circuit, the simulator makes a distinction between a run and a simulation. A run only allows us for a simulation that mimics the actual quantum hardware. For example, it does not allow for access to the amplitudes of the wave function of the system, since that is not experimentally accessible. Simulate commands, however, are more broad and allow different forms of simulation. When prototyping small circuits, it is useful to execute simulate methods, but one should be wary of relying on them when running against actual hardware. Currently, Circ ships with a simulator tied strongly to the gate set of the Google XMON architecture. However, for convenience, the simulator attempts to automatically convert unknown operations into XMON gates as long as the operation specifies a matrix or decomposition into XMON gates. This converter allows us to simulate any circuit that has gates that implemented 1 and 2 qubit non-matrix gates. Future releases of Circ will expand simulators. Okay. So because the simulator is tied to the XMON gate set, the simulator lives in contrast to core circ in the Circ Google module. To run a simulator of the full circuit, we simply create a simulator and pass the circuit to the simulator. Okay. So we're going to copy paste what it's doing, creating the circuit, or pen to pen. Key X, circ measure, circuit. Okay. So one step. So now basically we're doing these, and so we're running that, and we get those counters 0, 1, 32, 256, 128. I guess those are the decimal representations of our state, and this is sort of the frequency, and the ones that don't appear are just probably 0. Now that we have run this 100 times and produced a histogram of the counts of the measurement results, what are the keys in the histogram counter? Note that we have passed in the order of qubits. Note that we have passed in the order of the qubits. This ordering is then used to translate the order of the measurement result to a register using big endian representation. Okay. For our optimization problem, we'll want to calculate the value of the objective function for a given result run. For our optimization problem, we'll want to calculate the value. Exactly. So this objective function, this is what we are trying to minimize, I guess. For our optimization problem, we'll want to calculate the value of the objective function for a given result run. So those, exactly, this is not what we're solving for at the end of the day. This is, it just gives you the result of okay, one way to do this is to use the raw measurement data from the result. Another way to do this is to provide to the histogram a method to calculate the objective. This will then be used as the key for the return counter. So basically, the energy function. Okay, so this is what calculates the energy function. Okay, and basically we give that to the histogram object, so we can then okay, so we can then just directly display the energy function value as part of the histogram. Okay, so if we do this, def energy function. So this is something that I'll probably need to dive into. So what's the actual energy function? Is it just our Hadamard? Means least, reshape measurement into array that matches grid shape. Convert true false to +1, -1. For ij error, for j, jr, ij, total energy. -1, -3, 1, -5, 5 and 7. What is this? Okay. Then objective function is the energy. Hist is sort of so you get the histogram with the energy values, and that returns the expectation value. And that's kind of the caveat. That's what I was a bit lost with in the very beginning, because I didn't know what the expectation value really meant. So just save that. So if I do this, that basically what it does is it picks that, and then okay, so it calculates the mean. So it basically takes it sums all the values and then divides that by the number of repetitions. Okay, value of the objective function minus 0.98. Okay, parameterizing the ansatz. Okay, so I'll go back to this. Today I really wanted to get to the very end of the whole thing, which is almost there. So we're almost there. Luckily for us, we have written our code so that, sorry, here. Now that we have constructed variational ansatz and show how to simulate it using circ, we can now think about optimizing the value. On quantum hardware, one would most likely want to have the optimization code as close to the hardware as possible. As the classical hardware that is allowed to interoperate with the quantum hardware becomes better specified, this language will be better defined. Without the specification of a circ also provides a useful concept for optimizing the looping in many optimization algorithms. This is the fact that many of the value in the gate sets can, instead of being specified by a float, be specified by a symbol, and the symbol can be substituted for a value specified at execution time. Okay, it's alpha, beta, gamma. Okay. Luckily for us, we have written our code so that using parameterized values is as simple as passing symbol objects where we previously passed float numbers. Okay, so here you just pass those things. Okay, that's the only thing you do, and it just reuses the whole the same. Oh, that's interesting. Okay, so let's copy paste that. Let's copy paste that. Basically, okay. XX. What are those M's though? What are those M's? The measurements. Okay, those are the measurements. Because it seems like I don't have enough space, so this kind of gets... It's weirdly formatted. Yeah, okay, those are these M's here, I see. Cool. Now that we note that now the circuit's gates are parameterized. Parameters are specified at runtime using parameter resolver, which is just a dictionary from symbol keys to runtime values. Okay, parameter resolver, so you just do it like this. Resolved circuit. So, yeah, so you would just do something like that, yeah. And then print resolved circuit will probably give you, yeah, the actual numbers. Okay, cool. Okay, more usefully, circ also has the concept of a sweep. A sweep is essentially a collection of parameter resolvers. This runtime information is very useful when one wants to run many circuits for many different parameter values. Sweeps can be created to specify values directly. This is one way to get classical information into a circuit, or a variety of helper methods. For example, suppose that we want to evaluate our circuit over an equally spaced grid of parameter values. We can easily create this using linspace. Circ linspace, key alpha. So what it does is it starts at 0.1, stops at 0.9, and it does this in 5 steps. Is that correct? Results, simulator run sweep, simulator run sweep. Circuit. Okay, interesting. There's a bunch of interesting utilities in here to do that. So if I just, if I do something like that, okay. Oh, okay, so now it's done the, it's done. Okay, so first it increases gamma. When it's done with gamma, then it increases beta, and then once it's done with beta, it increases alpha. And it's done in 5 steps, right? Okay, interesting. So it's just a way to automate the executions of the circuit together with finding the minimum. Now that we have all the code, we need to do a simple grid search over values to find a minimal value. Grid search is almost definitely not the best optimization algorithm, but here's simply illustrative. yeah, I mean, I guess here you can just, plug in whatever gradient descent or whatever like algorithm to just, observe the results of something and then figure out how to modify the stuff. So this is so what does the minimum here does is, okay, it just goes through all the results and gives you the minimum, I guess. Yeah. Sweep size 10. If I go and paste that, what are we getting? Mean, non, mean perms, non. For resulting result value of subjective function result, if min is none or the value is smaller than the minimum, then update the minimum as a typical search for the minimum thing. It's not the most optimal thing, but it's just for illustrative purposes. And if we just run that and we wait a little bit, have a click run. I guess it just needs to find the minimal. Okay. Doesn't seem to. Doesn't seem to run. Anyway, so that's the end of it. Objective value. So okay, so I think the next intuitive thing is to understand what's the objective function. And how does this relate to the problem? Because we've got the circuit, right? So, and basically, so we've got the circuit that's the ansatz, and so how do this alpha, beta, and gamma then match to that energy thing and stuff like that? So let's try to take a look at the energy function first. So energy measurements, reshape measurement in an array that matches the grid shape. Stuff lists. So I guess and then produce a histogram that counts the measurement results. What are the keys in the histogram counter? Note that we have passed the order of the qubits. This ordering is then used to translate the order of the measurement results to a register using a big endian representation. Yeah, so that's the I assume the keys are the result of the measurement. The keys are the result of the measurement, and then how many times they pop up with 100 runs, right? This ordering is then used to translate good. So for attention problem, we want to calculate the value of the objective function. Okay, now so let's figure out what's the objective function. This seems to me true to false to +1 -1. True true, false, +1, -1. So it's translating. But why? What's true or false? So what? There's a boolean somewhere? Times age. So, but this is basically that Hamiltonian, because it's doing, so the total energy is going to hold the value, and then it's saying basically some PM mass, what is this? So it's summing that times h, right? So those are, remember, the energy fields. Time h. And then it iterates over the first j fields, the j row fields, and then it iterates over the j column fields. And so what it does is it does this value times whatever we've measured for this, whatever we've measured for these. Okay. Which basically, this is basically this part in here, right? This is the value we have, and this is what we've measured in one qubit and what we've measured in the other qubit. And this is the first part. So we're literally doing that. We're basically calculating that. Yeah, and then it does it for the rows. So basically, you do this for the two j fields we have, right? And it all adds up, and then that's your total energy. That's your total energy. 7, 5, 4. But what are the keys in here? Key X. Measurement on an array that matches grid shape. Okay, so we're literally we're actually measuring each qubit separately. Is that correct? Is that what we're doing here? We must, right? Because that's the idea. So literally we're measuring whether each qubit separately, whether they are 0, 1, true or false, and then translating those into +1 and -1. Okay. So we're measuring each qubit separately, but then I don't understand then what is this thing here. Counts of the measurement results. What are the keys? The keys that have passed the order are the qubits. The order of the qubits. The sorting is then used to translate the order of the measurement results to a register using a big endian representation. And this is the But it's like we don't care about the full measurement, we care about each specific qubit. So we're basically iterating over measurements. Okay. We're iterating over measurements. It's energy. Kx. I'm not so sure what the keys are. Fold function is the energy function. Key X. Okay, repetitions. Energy histogram. Energy histogram. The energy histogram is in here. Sum. So you're getting the key and the value. And we are actually doing key times value. What? How many times that energy pops up? So the energy 79 pops up 7 times. No, the energy 7 pops up 79 times. The energy 5 pops up 12 times. The energy minus 1 pops up 4 times. The energy 1 pops up 3 times. That's what it's doing. Okay. Those are the energy values. Okay, okay. So now the keys are here, the energy functions, the energy results, and then you still have the count of how many times those things pop up. Okay. And so with these, you basically then calculate the expectation value. Kind of that's what's the average energy value for that particular configuration based on 100 runs. Okay. I kind of feel a bit blocked in the sense that, okay, so this is, I understand this. But then what's the point of... So so what I know, what I understand now is that the circuit is not necessarily this. It's not that the circuit is not related to the and in this case the circuit, the answer is not related to the Hamiltonian. The Hamiltonian is basically your objective function. That I get now. The circuit is just something that represents your problem. So you're translating your problem into a circuit, and that's, I guess, the gist of QAOA. That you gotta find a way to represent your problem as a circuit. And then okay, this circuit should be then, you can parameterize it so you can explore. That's exactly, that parameterization is what kind of keeps me a bit hooked into why. Because it seems like we're not doing anything with those parameters at the end of the day. So we're just playing with them so that because the first step is the clear idea is the first step is you're getting to a superposition of all the possible. So you're getting the superposition of all the possible solutions, right? Then you let your circuit run, and then you kind of measure. So, but then how that particular circuit, you can tweak it a little bit more here and there. So you can then see what's the minimal energy. I'm at a point where I understand all the pieces, but I don't understand the big picture. As in, it's feels a bit like magic. That's just basic stuff in this case, right? So you can use whatever techniques and okay. But at least we've got until the end. I think one more video is gonna be the last. It's gonna be just, I think we just need one more video to dive into this. Running out of time for today, so but basically that's how that's how this looks like. So you're doing the energy function. That's basically your Hadamard. That's how you're calculating your Hadamard, and you're interested in finding sort of what's the lowest energy, or what's the lowest value, and then one way you would do that is that you would kind of use phase estimation, right? But that's expensive. So another way to do it is with VQE. That's still a topic to discuss a little bit about. Yeah, but that's your objective function, which at the end of the day, what you're doing is you're getting just the average. That's the expectation value. You're just getting the average of that. And then you're just playing with different parameters. And then you just get what's the minimal, right? So you can have smarter strategies probably on what's the next step. Here it's just the basic, just run through different possible configurations and check all the different possible, within some defined boundaries, all the different possible configurations of alpha, beta, and gamma. And that tells you sort of the minimal energy. But here you're not encoding a Hamiltonian anywhere, right? So you're building an ansatz, so you're building sort of a model of your problem using a quantum circuit. Whereas with a quantum phase estimation approach, you would still need to basically encode your Hamiltonian. And then by applying by applying quantum phase estimation using a controlled version of your Hamiltonian, you would be able to find what is the eigenphase of that Hamiltonian. What I'd be curious to know is that basically the that particular instance of circuit that gives you the minimal energy, that should be a possible Hamiltonian, should it? Or not? No, because it doesn't describe. No, because it doesn't describe the way the system evolves. It's not like here your Hamiltonian is the Hamiltonian here is the actual objective function. So the circuit has nothing to do with it. The circuit is just a representation of the problem. Okay, I got the basic idea intuitively, but I'm still missing. I'm still feeling a little bit far away from this. Okay, that's why this works. Especially the parameterization part is a bit like, is this really it? Like, is this your ansatz basically a model of your problem? That's the right question, probably. And so you're parameterizing that model. But the idea here is basically, you're getting, so you're first running the XPow gates, which I guess all the purpose of those is they put you in superposition. half turns. So, given the definition of the product instance, we now introduce our answers. Answers will consist of one step of a circuit made up of an X power gate for the same parameter for all qubits. This is the method we have written above. Yeah, but that doesn't. They don't explain why this is applied. Okay. Yeah, but basically that's the idea. It seems to be this. I'm stupid. I probably feel stupid. It feels probably stupid. I'm just repeating over and over again the same thing, but I'm not so sure if that's it. So what I understand is the ansatz is a model of your problem. It's a parameterized model of your problem. The first step here, it's not part of the model. It's more like you're getting into a superposition, right? And then you're running your model. And so and then at the end of the day, at the end of this, you just measure your qubits, because each will be a side. And then you say, good, so for that particular configuration, what's my energy function? And then you explore, by parameterizing the model, you explore different energy values, and then at some point you find what's your minimal, and that's what you're going with. I guess that's an approach to approximate that minimal value, because you cannot solve for that easily in a quantum in a classical computer. I think that's the point. I think that's the point. This is more of an approximation approach, right? And of course, it might find better models that will kind of give you more accurate values, but that's probably that's the beauty of this is the handcrafting of these models. Okay, that might be it. I don't know. I'll think a little bit about whether I can play with that somehow to see if I can understand this better. Maybe I can just Google a little bit more around, dive into QAOA to find what's the difference between QAOA and VQE, because that's still a bit confusing, but this seems to be like that. I mean, I'll publish this video and I'll ask the question in Twitter. Is the ansatz basically a model of my problem, a parameterized model of my problem? Yeah, that seems to be the right way to ask it. Cool, perfect. Then we're good to go.